I mean, when you do this testing for imbalance, right, what you are interested in the end is not, it's just an intermediate step, right? What we're interested in is estimating the average treatment effect, right? So, and how do you do that if you, for example, detect that some of your strata are unbalanced, right? What should you do? Should you drop them, right? And what are the consequences of doing that, right? So that's what we discuss in this paper. Everything is the same here, and now I'm a little bit more careful in terms of saying that you have Y1, which is the potential outcome of being treated, Y not being treated. I've changed the notation here, so PS now, I shouldn't have done that, but PS is the importance of each stratum. Observed outcome is Y, and what you observe is YT, X, and the stratum that you have. So say that we are able to compute and to consistently estimate beta S, which is AT for a given stratum. Okay? So how do you do that? I mean, you run a regression of Y on T given X, right? Or just take the difference between Y for treated and Y for controls. But then you average that, right? So that's theta is your parameter of interest. So the way that you're going to proceed is to construct some theta hat here using beta hat S and the proportion and the relevance of each stratum, right? So the null hypothesis is written in terms of potential outcomes, can be written this way, which is basically saying that for any given X, right, any given stratum, T is totally random, right? It's a result of randomization. Okay, so another way to say that we have that our H naught is basically valid is saying that this thing here holds, this equality holds, right? So let's do the following. Let me define this capital delta S, which is this indicator that this thing here in the population is actually true, right? And let me define this small delta as saying that I have some statistical criterion that says that some stratum S is well balanced. Okay? So I have some criterion here. So in the previous paper I had many different test statistics, but say that what we have here is just a F statistic, right? And you have some FC, say that you're going to say that at say 5% you're going to be happy to say that there is no imbalance in strata S if this F of S is more than FC, right? So this delta S is this indicator, is small delta S, right? So delta S indicates whether strata S pass a balance test, whereas this delta S is capital delta indicates whether this strata is balanced or not in the population, right? So those two things are different. So what we're trying to identify when we remove those strata such that delta, small delta S is 0, right? We can think of different parameters of interest, right? The ATE, of course, right? Or this ATE for the unknown balance population, right? Or this ATE for in the balance population in the sample, right? So typically what we want to do is want to estimate this guy here, right? The first one, right? I mean, you don't want to define your parameter of interest depending on your data, which is this one here. And you also don't want to define, I think that's not the thing that you want to do, to define the parameter of interest depending for this unknown balanced subpopulation. You don't know which strata have this property here, right? So the last one of these objects is a random function of the data. As I said, since this small delta s is non-degenerate for all the strata such that there is no imbalance, right? So this thing here has a distribution, right? And the second one, as I said, could be just, we are defining something for some arbitrary subpopulation which we don't know what it is. So in this paper we say that the researcher should be interested in ATE, right? But most of the results that you have will remain valid when the researcher is interested in estimating this ATE for the unknown subpopulation. So as I said, this delta S is going to converge to this distribution here, right? It's going to be a Bernoulli with probability 1 minus alpha of being equal to 1. And as the sample size increases, if for those strata that are in balance, this thing here should converge to 0. And I think now that, our main contribution is to consider, okay, in terms of inference, what we need to do here, right? So suppose that you have this thing here that you know how to behave, how that behaves, right? We know how to compute this beta hat S, right? And you know what is the asymptotic distribution of that. Let's say that's it could be either, that's that say the asymptotic bias here is 0, or that's consistent. Anyway, the problem is that we don't know exactly, of H naught, what is the bias that we're making, right? In terms of having this unbalanced stratum, right? Because we don't know exactly how differences in the covariates affect your estimation of AT within that stratum, right? We could have a model and so on, but let's take the view that we don't want to compromise, don't want to say anything about how X affects Y, right? We know that it might produce a bias, I don't know how exactly, but so that's why I'm testing for imbalancing in X, right? So what people typically do, remove unbalanced strata from the analysis, right? Because I know that if I keep those unbalanced ones, I may be producing some bias. Okay, so what happens with your AT estimator that only use the subpopulation of the strata that survive a balance test, so that survive this pre-testing, right? Let's call it theta hat, right? Where this lambda, which are those weights, are basically the weights for that you construct, right? You have to divide by this sum here, right? For those stratum that have delta as such that it's equal to 1, right? So remember that delta S is either 1 or 0, and delta indicates that pass the balance test, and PS is the proportion of each stratum. So that's your final estimator here, right? So what are the properties of this thing here? So doing doing this sort of decomposition here, right? And not multiplying to square root of n, which would be the thing that we would do typically, right? So what people would typically do would be multiply by square root of n in order to say that this thing would converge to a normal distribution with a given variance, right? What you show is that the rates of convergence is not a square root of n, right? Because of this thing here, right? Because of this difference between lambda and p. So let me be more precise. So the first part here converges at this rate. If you multiply by square root of n, it's going to be it's going to converge in distribution, so it's going to be limited in probability. But this thing here, at this rate, right, without multiplying by square root of n, has a distribution itself, right? And that's the problem here. It's not only that you are ignoring something in terms of your variance, right? The thing that is actually converging is lower is something that you're not taking into account into your analysis, right? It has to do with the fact that some strata may or may not, in a random way, end up in your final sample, right? And you're not taking that into account. So the main message of this paper is that, I mean, it's not a matter of correcting the variance, right? It's a matter of you're actually doing something that's totally wrong, because the thing that matters is this first part here. If n is super large, this thing here is going to go to 0 much faster than the second part here, which is going to converge to a distribution. So, and that's the key conclusion here, right? That this thing here is going to explode, right? If you multiply by square root of n here, right? So this thing here grows without bound, right? So what people are typically doing is not correct, right? Yeah, so that's another way to think, this intuition here. As the sample size increases, right, you sort of solve the problem of uncertainty of this problem here, right? But you still keep the problem of uncertainty here, right? It's like saying this thing converges in probability, right, to 0. You're nice here, but this thing here is going to converge in distribution. Okay, yeah, and then what we did, yeah, so in large samples you're more uncertain about which strata will be part of analysis than we are about the difference in mean outcomes between treated and control. What you should do in the end is the following. Okay, so let me just conclude and say I have one last point here. So pretesting and removing unbalanced strata induce the resulting AT estimator to be conducted in a random subpopulation, right? First stage uncertainty does not vanish asymptotically and dominates AT's estimation uncertainty as the sample size increases for any fixed alpha. A solution to this problem would be to let alpha goes to 1, right, as sample size increases, right? Which means that as the sample size increases, you can be, but then you're going to be more rigorous, right, in terms of detecting imbalance as the sample size increases.